We're now going to go into a little bit more detail on engaging with asymptotically linear estimators of parameters and using them to construct asymptotic confidence intervals for those parameters. Here, we will see that constructing those asymptotic confidence intervals will look very similar to constructing asymptotic confidence intervals for the population mean from the sample mean. All right, just a quick reminder about asymptotic linearity. Here, if we have n observations drawn identically and independently from some distribution f, and we have a parameter psi of f that we're trying to estimate and come up with an estimator psi hat n of f, a function of our data, we call that estimator asymptotically linear if this expansion here holds, if the difference between our estimator and the parameter we're trying to estimate is an empirical average of n IID terms plus some asymptotically negligible remainder. And in this case, in here we have phi of f, which is our influence function. That is some function that is mean zero, that has expectation zero under f. So when this holds, when this expansion holds, we say psi hat n is an asymptotically linear estimator of psi of f. Intuitively, again, we think of these as estimators that asymptotically look kind of like a sample mean or an empirical average. Asymptotic linearity is really, really useful. If our estimator psi hat n is asymptotically linear for our parameter psi, then so long as the variance of that influence function is bounded as less than infinity, we have that the difference between psi hat n and psi, our parameter, suitably scaled, has a Gaussian limit with mean zero, and the variance of that Gaussian limit in this case is exactly the variance of that influence function. And again, this is a formal way of writing things. Intuitively, we might think of this as psi hat n is roughly normally distributed with mean or expectation psi, that true parameter, and variance that looks like the variance of the influence function divided by the number of observations. Right? And again, this is informal, but I think very good for intuition. We're now going to try to use this for constructing confidence intervals. And just recall when this was a sample mean used for estimating a population mean, right? We had something like this, and we were able to use this to construct confidence intervals quite easily. We said, okay, our confidence interval should be centered at z bar n, and we should add and subtract multiples of its standard deviation, square root sigma squared over n, so sigma over square root of n, and the multiple we include in that half-width should be based on quantiles of a standard normal distribution, and in fact, often we don't know sigma squared, so we have to estimate it. And we are going to engage with the same thing here. We're going to center our interval at psi hat n. We are going to base our half-widths, the amount we add and subtract, on this variance, or really the standard deviation, sigma sub phi over square root of n. And the multiplier there is going to be based on a standard Gaussian. And finally, we're going to have to generally think about estimating this because we won't a priori know it. So more formally, if we have a consistent estimate of the standard deviation of that influence function, and we form an interval that, again, is centered at our estimator psi hat n, where we add and subtract a multiple of the asymptotic standard deviation of that estimator, or an estimate of that, where this multiple c beta is based on a standard Gaussian distribution, then we have an asymptotic level beta confidence interval for our parameter. So again, this looks like there's a lot going on here, but it's basically exactly what we were doing when we were forming confidence intervals for the population mean using the sample mean and the sample standard deviation. So that holds essentially equivalently when we're thinking about asymptotically linear estimators and using them to form confidence intervals for parameters. One tricky part here, however, is going to be getting this consistent estimator of the standard deviation of the influence function. So to estimate the standard deviation of the influence function, we could first estimate the variance of the influence function and then take the square root. And we know that if we have a consistent estimator for the variance of the influence function, when we take that square root, it will give us a consistent estimator for the standard deviation. So how might we think about estimating that variance of the influence function? Well, each of these phi of zi are independent and identically distributed, and in fact, we know their mean zero, so we could use an empirical or sample variance estimator. We could take each of these, subtract off its mean, square it, and look at the average. And in this case, this would give us maybe this candidate for our estimator. And in fact, this would be a really good estimator if we could calculate it, right? The law of large numbers says that this empirical average should converge to its expectation. And we know the expectation of each of these pieces is exactly that, not the standard deviation, but that variance sigma squared phi that we were interested in, and then we could take the square root of this estimator. However, we will see that there's a problem in trying to do this calculation. And the problem is that this quantity phi sub f of zi depends generally on elements of f that we don't a priori have access to, that we don't know, and we're going to need to estimate. So again, this estimator doesn't quite work, and we'll look at it in an example and see how we can modify it to make it work. So what's the problem here? Again, I said, this sub f here makes things tricky. And let's look at this in a very simple case, in the case of estimating the population mean using the sample mean. So in this case, our parameter is just going to be the population mean. We'll call it mu sub f. And our estimator is just going to be the sample mean, right? What we've called in the past z bar n. I'm just trying to stick with the general notation here. All right, so in this case, we have this, what is an exact linear expansion rather than an asymptotically linear expansion. And if we're using that proposed estimator that I said we can't calculate, what would we do? Well, this is the influence function, right? Phi sub f of z is z minus mu sub f, and maybe I'll just write that out, right? Our influence function is phi sub f of z equals z minus mu sub f. And what do we notice here? Well, we notice that there's a problem, right? This mu sub f is going to give us a problem. We can't actually evaluate this without knowledge of the parameter that we're actually trying to estimate. So, our originally proposed variance estimate would be, okay, take each of these, apply zi in each of those, square them, and then take the average. Well, can we do that here? No, because of this guy. We don't know what that is. If we knew what it was, our problem would be solved. So again, this would be a lovely estimator, but in fact, it depends on these parameters of the population that we don't actually know. So as we noted, we can't actually use this original estimate because it has parameters of the population that we don't have access to. So what might we do instead? Well, instead, we might take those parameters of the population that we don't know and plug in estimates for them. Right? So rather than trying to estimate the variance of the influence function as this average of zi minus the true mu squared, we say, okay, we can estimate it using zi minus an estimated mu squared. And in this case, the best estimate might be mu hat equals the sample mean, z bar n. And again, this is actually an estimator that we can calculate. It's only a function of the data. And in fact, we have shown that this estimator is consistent for sigma squared phi. Right? And so if we take the square root of this estimator, that will be consistent for sigma phi. So what does this mean more generally? So again, we're trying to estimate the variance of the influence function so we can then get a good estimate of the standard deviation of the influence function. And we generally can't use the most obvious proposal, which is just take the influence function, apply it to each observation, square it, and then average them, because this involves pieces of f that we don't have access to. So instead, what we do is we plug in estimates of those pieces of f. Sometimes those are called nuisance parameters. And I'm going to now denote that sort of estimated influence function by phi hat. And so once we've plugged in those estimates, then we can take that maybe estimated influence function, or influence function with estimated nuisance parameters, plug in each of our zi, square those, and average them. So, and this is generally the estimator of the variance of the influence function that we use in practice. And there's general theory that shows that this is consistent under very minor conditions. However, we're actually not going to engage with that in practice in most scenarios. So again, we're just swapping from using the actual influence function here, which we don't have access to an influence function where we have plugged in for nuisance parameters. So let's look at this in another example. So let's imagine now we're trying to estimate the population variance. And we estimate it with this sample variance. So again, recall that if we look at psi hat, our estimator, minus psi, the parameter we're trying to estimate, this has an asymptotically linear expansion, right? So we can write this difference as an empirical average of our influence function applied to each of our observations, plus this asymptotically negligible term. And so the question is, how can we get at the variance of this? Again, we don't know this mu sub f or sigma squared sub f. So what do? Again, we plug in best guesses for the parameters we don't know. So we get mu hat plugging in for mu sub f. We get sigma hat squared plugging in for sigma squared sub f. And then we can estimate the variance of our influence function by just taking this quantity, right, with these pieces plugged in, squaring that, plugging in each zi, and then looking at the average of those squares. And again, this will give us an estimate of the variance of our influence function. If we want to turn this into an estimate of the standard deviation of the influence function, we would just apply a square root to this whole thing. So I'm not going to go into detail here, although in this case, it's relatively straightforward to show that this estimator is consistent, does converge in probability to the variance of the influence function. And thus, if we take a square root, then the corresponding estimator will converge in probability to the standard deviation of the influence function. And we can then take this and create, say, a 95% asymptotic confidence interval for the population variance, which was that original parameter of interest that we were engaging with. And so again, just to return to big picture, this says quite generally, whenever we have a parameter of interest psi and an estimator psi hat, and we would like to form a confidence interval for psi around psi hat, the key is to look at that asymptotically linear representation, to understand what the influence function is, to note where there are pieces of that influence function that involve parameters that we don't know, to plug in estimates for those parameters, and then to calculate sort of an empirical variance using those estimated parameters plugged in for their population counterparts. So one tricky piece that we're not going to engage with in too much detail in this course is really generally showing consistency of these estimates of the variance of the influence function, where we've plugged in a version of our influence function where we have used estimates for unknown parameters. It's a bit beyond the scope of this course. It requires a little bit of empirical process theory. In general, so long as you estimate these nuisance parameters, or whatever parameters you have to sub out here, reasonably well, then this estimator will be consistent. But again, that formal calculation is a little bit beyond us. I think the idea, though, is quite important and quite useful. This is sometimes referred to as an influence function-based estimate of the standard error. And in addition, this sometimes lines up with what people refer to as a robust standard error.